Welcome everyone to what I consider the most high-stakes negotiation in your entire workflow. In our previous units, we breached the cell and opened the vault. But now, we face a new, invisible enemy. You are looking for a small molecule, perhaps a drug candidate, a metabolite, or a trace toxin, and it is currently surrounded by a massive, rowdy biological crowd. If you've ever felt like your data was just a flat line despite knowing the analyte was there, it's likely because the crowd was too loud. This unit, Crashing the Gate, isn't just about laboratory cleaning. It's a tactical masterclass in removing the biological bouncers that block your signal. Have you ever tried to hear a whisper in a crowded stadium? It's nearly impossible, no matter how good your ears are. In mass spec, your small molecules are that whisper, and the proteins are the 50,000 screaming fans. A common technician error is thinking the instrument can simply filter out the noise digitally. It can't. If you don't physically clear the stadium, the ionization source gets overwhelmed, and the signal is lost in the chaos. We don't just want a clean sample, we want a silent background. By mastering the art of the crash, you are essentially turning off the stadium's PA system and sending the crowd home. To clear the stadium effectively, you need to choose the right strategy. We categorize our protein clearing techniques into 4 strategic roles. First, we have the solvent sniper, acetonitrile, and methanol, which we use for precision and speed, especially in clinical drug monitoring. Second, the acid attacker TCA, for when you need a total, instant structural collapse of the protein crowd. Third, the salting out strategist, ammonium sulfate, a gentle giant that uses the physics of water molecules to win the battle. Finally, we will wrap up with the decision matrix, the specialist's guide to choosing the right weapon. To understand how to throw a protein out of the room, you have to understand why it's allowed to stay there in the first place. Proteins are comfortable in your sample because of the hydration shell. Think of this as a protective layer of water molecules, held tightly by hydrogen bonds, that acts like a life support system. As long as that shell is intact, the protein remains soluble and dispersed. Every method we discuss today has one singular mission: to strip away that protective water layer. When the water is gone, the proteins become naked and hydrophobic. They aggregate into heavy clumps and crash to the bottom of the tube. Organic solvents like acetonitrile and methanol are the specialist's sniper. But here is the secret most beginners miss: the critical volume ratio. Look at the data on your screen. If you only add a 1-to-1 ratio of acetonitrile to your plasma, you're only removing about 30% of the proteins. That is a disaster for your LC column and a death sentence for your sensitivity. But the moment you hit that 3-to-1 or 4-to-1 ratio, the efficiency jumps to over 96%. Why? Because the solvent shifts the dielectric constant of the solution, effectively pulling the plug on the protein's hydration shell. Sometimes, you don't have enough sample volume to use a 4-to-1 solvent ratio. This is when you call in the acid attacker TCA. By dropping the pH far below the protein's isoelectric point, you force the proteins to carry a massive positive charge that disrupts the hydration shell instantly. TCA is incredibly efficient. It can hit over 90% protein removal at a tiny 0.5:1 ratio. However, actually, here is where 80% of small molecule projects fail quietly: acid sabotage. If your target molecule is acid labile, TCA will destroy your gold while it's killing the proteins. Audit the stability of your analyte first. Imagine the ions from ammonium sulfate as water thieves. They are so chemically hungry for hydration that they literally steal all the available water molecules away from the proteins. The proteins, left thirsty and naked, have no choice but to aggregate and precipitate. This is a gentle method, but here is the mentor's warning: don't bring salts to an ESI party unless you want to kill the signal. Non-volatile salts are the mortal enemy of your ESI source. They cause ... and drop sensitivity to 0. Amateurs foul the source. Specialists protect the hardware. Let's put this architectural logic into practice. Every time you face a new sample, you need to audit your choices. Are you working with a high-concentration drug in plasma? Your go-to is the solvent sniper at a 3-to-1 ratio. Are you looking for trace metabolites where every microliter is precious? Call in the acid attacker, but double-check your analyte stability first. Do you need to keep some proteins alive? Use the salting out strategist, but make sure you have a plan to protect your MS source. A pro never starts a precipitation without knowing exactly what they are willing to sacrifice. We have successfully crashed the gate. We've learned that protein precipitation isn't just a manual chore. It's a tactical removal of noise that allows the truth to emerge. We've mastered the solvent sniper, the acid attacker, and the salting out strategist. But as you head back to the lab, I want you to carry this specialist mantra with you. Purity is not about what you keep. It's about what you have the courage to throw away. If you are afraid to crash out the matrix because you fear losing a little recovery, you will end up with a sample so dirty that you see nothing at all. Have the courage to clear the stadium. The gate is crashed. The stadium is finally quiet. But look closely. There are still a few VIP interferences, like lipids and salts, that are hiding in the shadows of your sample. To get them out, we need something more surgical than a bulk crash. We need a selective filter. Join me in our next unit, Module 2-5, the selective filter, where we leverage solid phase extraction to turn those dirty samples into pristine, publication-ready data. You've unlocked the vault, you've cleared the bouncers. Now let's perform the final surgery. Any questions before we move to the next mission?